Maude Lemaire, who came to us from Slack. And she's been solving scaling problems at Slack for close to 5 years at this point. And she recently wrote a book about her experiences called Refactoring at Scale. And I believe she's coming with a very, very exciting topic to us about how they measured how far they can push Slack's technology. Maude, welcome to Craft. The stage is yours.
Thanks, Akash. Really appreciate it. All right, so today I'm going to talk about some of the load testing solutions that we've built at Slack over the years, specifically focusing on the most latest iteration of some of the tooling that we've built, which we've called Koipont. As Akash mentioned, my name is Maude. You can find me on Twitter at QCMode. I have been at Slack for almost 5 years now, so I've seen the team grow from just over 100 engineers to now over 800. It's been kind of a crazy transition, but it's been a really fun one. Most of my work in that time has been focused on really big refactors, a lot of them dealing with scaling and performance problems. That's really what gets me going, is really big scaling problems, making sure that we can get that next really, really big customer and make them really happy. I also recently wrote a book. There's a link which, when you get access to the slides, you can click that link and head over to O'Reilly and get that book if you're curious. There's a bunch of really great information about all stages of big refactors, everything you should be thinking about at every point. But there's also probably some stuff in there that even if you're doing like a small team refactor, you might find useful. So make sure you check that out. And because we're all sort of distributed around the world right now, I spent 4 years in San Francisco working for Slack in their HQ. And then I recently, during COVID, actually permanently relocated to New Hampshire. I'm originally from the East Coast of North America. And it's really nice being back in the trees and away from the city after so many years. All right, so without further ado, let's get right into it. This story might sound really familiar to a lot of you who have worked at small companies that have scaled up pretty dramatically in a short period of time, or maybe you're in that stage right now where once upon a time, you have a big customer, and in our case, we will call them Big Corp. And Big Corp is pushing the boundaries of yours, or in our case, our systems. And both of us were really nervous to opt them into more features because, well, given this was a normal day, just using a subset of our features, we were sort of worried about what would happen if we opted them into more. Most of us have had that experience of there's that one customer, right, that overshadows all the others, and they're the ones triggering all of our alerts and, you know, blowing up the CPU on our servers. And they're also giving us a lot of money, so we have to make sure that they're very happy. This is Big Corp. Normally, if we were in a big stage setting, I'd ask everyone to raise their hands if, you know, they could think of this customer off the top of their head. But for now, just picture a room full of people with a lot of raised hands. So in our case, Big Corp thankfully really liked Slack, and they wanted to use it more. This was both a blessing and a curse, because obviously we wanted them to use it more, but we were still a little bit small and scrappy, and we were afraid of blowing up our servers even more. So we didn't have the big company resources that like the Microsofts and the Googles of the world have with regards to maybe let's just create a team and like start load testing something, or let's spin up an entirely distinct separate version of our production environment and just like throw a bunch of traffic at it and see what happens. Like we didn't have the resources to do that. But we knew we needed to load test in some way. And so we built something. And the shape that took was what we ended up calling API Blaster. And basically all it did was it just issued a bunch of curled web API requests to our servers. If you're familiar with the Slack API at all, This might look very familiar to you if you've written a Slack bot before, slack.com/API, your API method, and a bunch of arguments afterwards. The team that wrote API Blaster at Slack actually wrote a blog post about it, which is linked in these slides as well. There's a bunch of other blog posts and resources linked throughout. So I do recommend that after the talk, when the slides are available, you're able to go check those out. So there's more details in there. I won't go into all the variables of other things that it sort of did, because that's sort of out of the context of this specific talk. But if you're curious, that blog post is there. Unfortunately, this tool didn't really test a critical component of our infrastructure, and that's the WebSocket stack. And to illustrate what I mean by that, we'll need to do a quick sort of high-level overview of Slack's architecture. Fair warning, this is very high level. There's a lot more complicated stuff that goes on under the hood, but for now, this will do. So on the far left, we have all of our clients. That's the yellow box. We have things like the desktop app, the browser, if you access Slack through your browser, the iOS app, the Android app. Once upon a time, we had a Windows app. We do not have that anymore. But think of all of our clients, they're all here. These are the things that we develop in-house at Slack. These clients all receive and send information to all of our systems via 3 distinct APIs. So first we have the RTM, real-time messaging API. That is the API that's responsible for establishing and continuing to persist that long-lived JSON WebSocket connection. So if you didn't know, Slack establishes a WebSocket connection with our systems. That's how you're able to get those live messages and those notifications coming in. And it's a much nicer way than to pull our systems every couple milliseconds to make sure that messages are coming in and you're getting those notifications. WebSockets are great. Then there's the Edge API. So the Edge API is responsible for requesting data from our Edge caches. So there's a bunch of different points of presence where we have deployed this Edge cache throughout the world. So say you're using Slack in Japan, your client will be requesting cached information about your team, the users on your team, the channels on your team, all of that stuff from servers in Japan, which makes that much, much speedier, makes your client much quicker to respond, and you won't be as annoyed if it takes forever when you're trying to quick switch between one channel and the other. And then finally, there's the web API. So this is what API Blaster hit. This is probably the API that most people who have used Slack and or written a Slack bot or any sort of integration are really familiar with. That's your regular slack.com/API endpoints. And those are responsible for querying our main backend systems where most of our business logic lives. So there are these 3 APIs. That first link links to our public documentation about the RTM API. You can establish a long-lived WebSocket connection with Slack if you would like to. We actually recently made improvements to that. The web API link also links to our web API resources. And then the Edge API link links to a blog post about our Edge cache from a couple of years ago, but it's still really good information. All right, so we have this high-level overview. The dotted red line is what API Blaster tested in terms of surface area of our systems. So basically what it did is it pretended there were no clients, and it just hijacked that connection directly to our web API and just made requests directly to our backend business logic systems. And there were no connected clients at any point. And so that meant that the real-time services in that teal box, that right here, that were responsible for sending content back over that WebSocket, they weren't, half of them weren't active. They were receiving information, probably, but they weren't distributing that information. The outflow wasn't happening. So to further illustrate this point, I'm going to talk about what happens when you send a message with Slack, and then you'll see how that goes through the system and why this didn't quite cut it. So, okay, I'm logging on in the morning to Slack. I go to the general channel, I'm writing good morning. What happens when I do that, and this is, I'm gonna hand wave a little bit because there's actually way more that happens under the hood. Slack is now a very complicated piece of technology, but I'm happy to answer some more specific questions during the Q&A if anyone has more specific questions about what happens at this point. So at a very basic level, there's a web API request that gets made to chat.postMessage. It sends this request to our backend systems. Then it writes that message to the database. Once that's been persisted and the backend systems are sure that that message is persisted in the database, then what it does is it sends out a message to the real-time services. These are systems that's the teal block in the diagram again. They maintain all the active WebSocket connections with all Slack users across the world. And those are organized by channels. And so let's say we're both in the general channel. These real-time services know that we're both in that channel and we have active WebSocket connections with that channel. And what that's going to do is these backend systems are going to send that request up to the real-time services system. And then those will propagate that message right back through to all the connected clients. And that's how Akash, if he's in the same channel as me, will get good morning and see my message. So this entire top piece was not being exercised at all by API Blaster. And that's actually a really, really important critical piece of our infrastructure because we can have massive message fan out. If you're sending one message to our backend systems and there's only one connected user in that channel, then there's only going to be one message sent back. But if you're sending one message to that channel and there's 100,000 users actively connected to that channel, then that one message turns into 100,000 messages being propagated back through that stack. So it's a really, really component to be able to test as part of our infrastructure. So API Blaster was okay trade-off for a while, gave us some amount of ability to like sleep easy at night, but like not really. And then that's when even bigger corp came along. And we'll like pretend that this is very true. Like with big corp, even bigger corp also really liked Slack. And what they wanted to do specifically was to house all of their users, about 100,000 of which of them were active on a weekly basis in a single channel. And at Slack, we mostly care about weekly actives or sometimes daily actives because those are the users that actually cause load to our systems. If you're provisioned and you never use Slack, that doesn't really impact us in any real way. So in this case, API Blaster definitely wouldn't cut it, right? Because we wanted to be able to test what the activity in that channel would look like and the fan out. So that whole like one message turns into 100,000 messages being sent over the WebSocket piece. So because even bigger corp wanted to understand that impact, we built another tool. This one we called Puppet Show. And this one enabled us to actually test that connection. So what it did is it simulated clients. And by doing just that piece, we were sure to have the full connected flow and test the entire surface area of our infrastructure. And we called each of those fake clients puppets. You know, pretty typical name of what you would expect for a system like this. So the tool, the way that it worked is it spun up thousands upon thousands of headless Chrome instances and logged them into slack.com/messages, which is how you would access Slack in the browser the regular way. And then the puppet master, which controlled all of the puppets, would send it scripts, send each of those puppets scripts to execute. So say, okay, I want the browser to switch to a channel and send a message. So say I want it to switch to general channel and send good morning. We could send that script. It was just a simple JavaScript script because these are headless Chrome instances and they're running slack.com. We could just tell them, do this thing, and they would do it. The problem was, even though it gave us incredibly high fidelity and it tested the RTM API, it also tested the Edge API, which API Blaster again didn't test, right? We were not making requests out to our Edge cache at all. There were no clients. So the problem was, I don't know if your computer runs a little hot when you're running VS Code, iTerm, Zoom, 150 tabs of Chrome and Slack at the same time. But imagine running 100 instances of Slack all on the same machine, logged into different users that are very active at the same time. It's not fun. Your computer will not have a good time. And as much as we were trying to toggle all of the resources that we were giving to, and this was distributed and deployed via Kubernetes across a bunch of different pods, as much as we were tweaking all of the different configurations to figure out what's the right amount of CPU, what's the right amount of memory that we need to give each of these instances, it was incredibly expensive and really, really hard to manage. And the fact that we had to spin up over 100,000 of these made it not fun on multiple axes. So the way that it turned out is, I think in the end, it was costing about 37 cents per day to run an individual client. So at the end of a week of testing, running through all the test cases that we wanted to verify for this customer, it ended up costing us like over $250,000, which was like a silly amount of money. So once we'd done that, the tool sort of lay dormant for a while because we were scared to spend that much money again. So about a year later, we decided to set this really ambitious goal, and we wanted to support 1 million users in the same Slack team by June 2021. It is now June 2021. So I'll tell you how we got there, and this was set about a year ago. Basically what we decided was we have all of these tools that we've built already. We have a lot of existing infrastructure. We have prototypes. We've learned a lot of things from our previous load testing experiences. What can we do? So basically what we took is we rebranded Puppet Show, and instead of having headless Chrome browsers, we spun up these lightweight client simulators that we wrote in Go. The idea was that hopefully they would be computationally much less expensive and easier to spin up and manage. That was the hypothesis. We hoped the hypothesis in science would prove us right. So here's how Koi Pond works in a nutshell. A Koi is a single Slack fake client, and it's a single Go subroutine. It's being controlled by a school. So the school is the top level Go program that spins up to 5,000 Koi. And that single Go program is deployed to a single Kubernetes pod. The keeper is what manages the entire state of the load test and manages those connections with those schools and checks in with them periodically, makes sure that all the work is being distributed and being executed appropriately. And so basically what that diagram, the puppets became, is this. We just replaced puppets with Koi. So this is the fun bit where I get to hope that the live demo goes well, which is always a risk with these things, but we'll see. Let's do it. So, okay, I'm spinning up a new load test. You can see that we don't take ourselves too seriously and we made everything Magikarp themed. So I'm going to do craft conf demo. I'm going to run the test until manually stopped. We use pre-generated tokens. I can go into a little bit of more detail about that in the Q&A if folks are curious. I'm going to run it on 1% of all of these pre-generated tokens across this team of about 2.5 million users. So for the sake of this demo, I'm only going to spin up about 25,000 users, and I want to do it a little bit quicker. So I want to spin up 2 schools at the same time. 5,000 Koi per school, and I'm going to start that load test. So what we can see is we now have this load test running. It's currently booting up some schools. We'll come back and check on this later. But what we'll end up seeing in our dashboards is we'll eventually start seeing simulations running, and we'll start seeing them take some actions. All right, so I'm going to go back to the presentation while this boots in the background, and we'll come back to it in a little bit. So with Koi, we define 2 kinds of work for them to execute. We define behaviors and we define formations. And the way that these work is that a behavior is an action, a specific action that a Koi can take on a permanent basis with a specific frequency. So it's usually just a single API call like chat.postMessage or conversations history. And it's made up of 2 different components. So it's made up of a frequency definition telling us how often to do it, and an implementation to actually tell the Koi how to do this thing. Because remember, they're not real Slack clients. They have no sense of how Slack actually works. They have to be told what to do. One thing that a team always talks about is they're dumb Koi. They have no actual real clue what anything is going on. They have a very basic understanding of what Slack is. So that's how it goes. So this is the frequency definition. So conversations history is a really good example. Is one of our most called APIs. All this says is within a given minute, there's a 10.8% chance that conversations.history will be called by 1 Koi. So the Koi will just loop through this entire list of behaviors and pick one at random, depending on the frequencies that are defined there. And then if we look at the actual implementation, so we have this piece of our configuration file that we call sequences, which is made up of definitions for each of those different API calls that we can make, each of those different behaviors. And in this case, this is the implementation for conversations history. So we have a doc because documentation is great and it's nice to be able to know what the heck this thing does when you look at it in a really large JSON file. So it tells us that it calls the conversations history endpoint. And then it has a series of steps. This one's pretty simple. It just has one step. It makes a call to the web API to conversations history, but it has a couple different pieces. So there's, again, a doc for the individual step because it's really good to know what each step does. And then it has a set of pre-actions. So we used Go templating language to be able to do this because, again, the Koi are really dumb, don't really know anything about Slack, but we have to be able to tell them some things and they have some sense of a couple of different Slack specific things so that they're able to take these actions more efficiently. So in this case, somewhere in our code, we've defined a function called random channel. And we are using that function called random channel to set a channel into this variable, this intermediate local variable called channel. If we're not able to find a channel, then we just like kill that sequence and we return and the Koi tries to do something else. Otherwise, we set the Koi's current view of the world, current channel. So like if you're in the client and you swap to a channel, we set that channel to this variable that we've set to channel. So basically the Koi have this very tiny, very succinct like client model, tiny little cache where they sort of know some things about Slack. And then we actually have the request piece. So that's where we call out to the web API with conversations history, and then we define all the arguments that we want to make that call with. So in this case, we get the channel ID that we fetched, and that's what we propagate into that channel field. And then there's a bunch of other arguments that we can send to that API. And then there's some actions we can take once we've received a response from that API. So in this case, conversations history gives us a bunch of messages from the channel and information about some users in that channel. So what we're going to do is we're going to greedily uptake that information into our little Koi client model, and we're going to add messages to its history, and we're going to add a bunch of user IDs so it knows about more users. And then it can take more actions based off of that information later. So that's a simple behavior. And these are all of these things that Koi are just automatically doing upon boot. There's a huge list of these, and I'll show a quick overview of how big this default config file that we use is. All right, and then there's a second piece called formations. So this we built later, and the idea is that you can take multiple actions, a certain percentage of Koi will take those within a specific period of time, mostly to simulate thundering herd behavior. So for example, take like a company CEO posting in the general channel, telling everyone to take the rest of the day off. And this company has like 300,000 people in it, and a bunch of them are active. So in the seconds following everyone getting that message, probably everyone is going to switch to that channel, go read the message and either react to it or thread off of it or something, right? And this is really common in Slack. We get these thundering herd behavior, and we have to be able to test for those because it's a huge influx of load to our systems in a really short period of time. And that's just like having background noise, which behaviors provides us with. This is a really key component to be able to test with high fidelity. So again, these formations are made up of sequences. The same concept that we used with behaviors, we're reusing again with formations. So this is a sample formation, sorry. There's a couple different pieces going on. So obviously we give it a name, and then we give it a duration of time that it should run for, and the number of active Koi that should run that formation. So in this case, what we're saying is 1% of active Koi. So say we booted up 25,000, we only want 1% of those to run that formation, and they should all have run it within 6 minutes, so 360 seconds. That tells us, that gives us a couple different axes to like run that thundering herd behavior on. Either we want 100% of them to run it within 10 minutes, or maybe we really want to test our systems and only run 100% of it within like 2 minutes and see how much everything explodes. We can do that with these two different variables. And then again, we have this similar structure where we have a set of pre-actions, an API that we call, And then additionally, we add this delay after milliseconds call, which enables us to actually define how much time should be elapsed between these steps. We don't want Koi to look like robots. And so we need them to actually look like clients. And by setting a time delay between steps, we can simulate that. Because human users of Slack are not going to switch to the channel, immediately mark it as read, and then immediately react within 50 milliseconds. It's just not going to happen. And so we have to be realistic with when these steps are happening. All right, so this formation has a lot of steps because, as you can imagine, the client does a number of different things when you switch to a channel and you react to the latest message. It fetches a list of users in that channel. It subscribes you to their presence. It does a bunch of other stuff. This is a very condensed version. But then the final piece of that formation is it actually adds that reaction. So it'll pick from the list of fish, ocean, and whale, and add a reaction to whatever we've set in that local variable message timestamp, which we previously set in earlier steps. So this is how they all build on top of each other, and we create this like tiny, really self-contained model view of the world, and we're able to take these actions. All right, so let's check back in with our Koi. And if I refresh this page, we'll see that we have a bunch of active schools. Most of them are at full capacity with 5,000 users. One of them, obviously, we weren't doing a full even 25,000. So one of them doesn't have the full 5,000 running. If we go back to Grafana, we'll see that within a couple minutes, we booted all 25, close to 25,000 of them, let's say 24,000. And then we can see all the web API calls that they're making with those different frequencies. And so in any given moment, it looks like getting the new WebSocket URL is the most popular API. That's one it's called really, really frequently. So that makes sense with our frequency configuration. Again, conversations history is at the top of that list. Like I mentioned, it's called very frequently. When you're switching to a channel, that's the first call that it makes. And so that makes a lot of sense that that's something that we simulate a lot. There's varying amounts of API failures. We see different errors depending on whatever's happening on our systems at that time, but also specifically on that team. Usually if these get really high, we end up investigating. Then these are requests to our edge cache, similar concept here. And then these are behavior calls overall, selection of random channels to see how distributed that is, because that's another axis that we want to make sure we're being honest on is folks are switching to DMs maybe more frequently than they're switching to random other channels or channels of different sizes. That's really important. And then we have some WebSocket information. So I think there's a little bit of lag on our prom systems. We have our own prom cluster specifically for load testing because we've overloaded our prom clusters with the amount of data that we've populated from these tests before. So sometimes prom's a little bit laggy, especially in the morning. So we might not get all the data, but it looks like we are seeing some data with regards to our WebSocket connections. And we're seeing how those are distributed in terms of connections being made across our different schools. And there's a bunch more data that we could dig into here. But I'm going to hop over to our configuration file just to give you a sense of how many different behaviors these Koi are executing in any given point. The list goes on for a long time. Then this is how we're able to get really high fidelity. All right, so switching back to the slides for one last bit, and then depending on time, we might be able to look at something else. So were we successful? Our goal was to hit 1 million Slack users simulated in a single instance by this month. I can say a resounding yes with a lot of confidence. So we started development in June after doing some tech specking of last year. In July, we managed to run a behavior-only test with 50,000 Koi. And then a week later, we were able to scale that up to 500,000. Remember that Puppet Show was about 37 cents per client per day in terms of cost. Koi cost is under 10 cents, under 1/10 of a cent per day per client, which is a huge, huge win. Then we built formations, which we talked about a little bit later, enabling us to have even higher fidelity in our systems in our testing. And then in October, we ran our first successful test with 1 million koi. We followed that up with 1.7 in December. And don't read too much into the timeline. The idea is that we worked on a bunch of different features all at the same time. Once we hit that October deadline, we were pretty convinced that we would be able to hit 2 million pretty heartily. And so we started focusing, shifting our focus to user adoption across the broader organization. And so that's why we only got to the 2 million test in April. But 2 million is double where we were supposed to be this month. And we had pretty good fidelity on that test. And so we're pretty sure that Slack can scale pretty darn well at this point. So, there is a recent blog post with a lot more details about some of the stuff that I went into that one of my teammates recently wrote. She goes into all the bugs that we found and we fixed as a result of all of our testing, future development plans, everything that we're working on in the future with this. And it's just a really great post overall. I highly recommend you go out and read it. As always, Slack is hiring. We seem to be perpetually hiring. If you want to check out our job listings, they're also going to be linked in the slides. But with that, I am going to turn it over to this one last view of this team that we do a lot of testing on. And you can see, I could maybe run the formation depending on how the Q&A goes, but you can see that we've run it quite frequently over the last couple of weeks. And these are all the koi reacting to these messages. So that is all automated and happening without anyone really doing it. It's really, really neat to see it in action. And you can actually see, because we're running the formation right now, and this is all local time from this morning for me, but you can see that they're posting in different channels, which is really fun. So that's how you know that it's working, which is really, really cool. It's actually having real users in those places. All right, and I think that's the bulk of what I wanted to cover.
All right. Amazing talk, Maude. I almost forgot to show you that you had 10 minutes left because I was very invested in your talk. Thank you so much. This was great. And I believe we have a good number of questions rolling in the Q&A section. So if you don't mind, we'll jump right into that. So the first question, I got a couple of outputs, is from Dominic. It's scrolling around a little bit. Okay. The question is, couldn't you just simulate less clients with more heavy usage, no delays, instead of simulating lots of clients with lots of delays?
The reason we can't do that is because of that fan out piece. So because one message can turn into 100,000 messages being fanned out, and that piece is dependent on the number of clients connected, that's why we need those active connections. One user being really active doesn't translate to the same impact in terms of outflow from our systems as 10 users not being super active. It's not a one-to-one sort of approximation that you can make, and that's why we need to actually have those active client connections.
Yeah, so you were more aiming for this catastrophe situation of the CEO announcing that everyone is off tomorrow.
Yeah, which we've run a couple scenarios of CEOs at really big companies running Ask Me Anythings, which are very popular channels and get a lot of traffic, especially in terms of threaded messages. And we have confidence that having 200,000 connected clients all reading from the same thread and getting messages from that, let's say, one user that's asking a lot of questions, we can actually withstand that really well.
Thank you for the answer. The next question that I see in front of me comes from Zoltan. Which parts of the architecture needed the most refactoring/scaling to handle this load?
Ooh, that's a really good question. All right, let me pull the slides back up. So there were a couple different pieces. I'm going to go to this slide because it is the most generic one. So we'd already done a lot of focus over the years on insane amounts of flow to our database systems. We'd also just done a migration to the test, which enabled us to more evenly distribute data. If you don't know about the test, there's also a really great Slack blog post about it, but it's basically a layer that enables us to do dynamic sharding on top of MySQL. So we've done a really big migration there. We've already done a lot of focus on making sure that those systems weren't overloaded over the years. Like in 2017, I was involved with a lot of that work, so that was good. The two pieces that needed the most amount of work were some of the real-time services stack, in that there's a concept of splay. So there's two different pieces in there, which I didn't zoom into that, but there's something called the gateway servers, which are the systems that are in charge of actively maintaining those WebSocket connections. And then there's channel servers. Those are the servers that have a one-to-one channel mapping. So the general channel that we were talking about is assigned to one channel server. That server is in charge of filtering all of the messages for that one channel. And you can see that like the server that is responsible for our biggest customers, everyone is in it channel, probably only has that one channel and like one other tiny one on it, because otherwise it was just like overflow with traffic. So those two systems, we really need to tweak the splay on the one that maintained all the active WebSocket connections, because that's where all traffic ends up going through in terms of all of the channels on those teams across all those users end up in that one place. We need to increase splay, so we need to add more servers there. We also found out that we had in production to increase our Prometheus cluster, because turns out that all of the downstream systems that we were using to log when we were doing those 500K user tests had a hard time catching up. Turns out when you have 500,000 active users on the same team, it blows up your metrics. So we had to grow those, but those aren't pictured here. And then there's a bunch of rate limits that we ended up adding in the business logic in our backend systems. So things like making sure that people weren't spamming threaded streams in Slack, because of, again, that relationship of one user sending a lot of messages to 200,000 connected users, that turns into the number of messages times 200,000. And so that ends up being a lot of influx to the real-time services stack. And we have to make sure that they're able to actually withstand that, both from the channel server perspective and the gateway server perspective. And so we added a bunch of rate limits there, which again, very unlikely that we will ever hit. But it's nice to have that prevention in place just in case something happens.
Yeah, it's a useful thing to have rate limits, I think, in general. Thank you for the answer. There's another one from Anonymous that the beginning of the question is very similar. It says, did you find areas of improvement to be made in the Slack code base while you were doing the load testing? But there is another question at the end of it. How did you monitor it, and did you use other tools than Grafana?
Grafana is definitely our main monitoring tool. There's obviously a lot of graphs that we keep track of in there, and actually making sure that that dashboard is snappy and not consuming all of my computer's CPU at any given point is a constant battle. We have a bunch of alerting plays that's also Grafana focused. But one thing that's really neat, and I can't show because I can't show our company Slack, but we have a bunch of different channels, as you would expect from someone who works at Slack, where all of our alerts go. And it also tells us when each school is booting, with how many tokens it's booting. And it's also telling us the state of the given load test at any given point. And so we have all of that. Basically, all we have to have open when we're running a load test. And right now, like, it's gotten so safe. Like, there's a bunch of ways that we can just see errors coming in. We're just like, cool, turn it off, whatever. And all the clients shut down within milliseconds. Like, the time, the drop off is significant. And actually, it took some of our downstream systems owners a couple of seconds to be like, wait, like a bunch of clients just dropped off. Like, are we okay? Are we having a bad time? It's like, no, we were running a load test. Like, it's fine. Like, you're okay. And they're like, okay, well, I was worried we lost like a whole team there. And it's like, yeah, you did, but like a fake one that like doesn't have any real users on it. So you're okay. But yeah, everything, the only things that we need to have open at any given point are Slack and Grafana, because everything is piped through all of that.
Okay, sounds good. Thank you, Maude, for the answer. The next question is, How do you give feedback to feature teams when you notice that some deployment or commit has damaged the preferred maximum load of your systems?
Yeah, that's something that we're actively working on improving. So we've been partnering with product development teams to write formations for different features across Slack. That's mostly to test that thundering herd behavior. So workflows is well, I guess it's not a new feature of Slack anymore, but it was newer maybe a couple years ago. So we wrote a couple workflows, workflow formations rather, to make sure that we could withstand load for that. And we partnered with that team. The team that's in charge of reactions and sending messages, we partnered with that team and they own their own formations. So that's the relationship that we've been developing with those teams across product. We still have a long ways to go to partner with more teams and build more formations and have this like more holistic overall test coverage. But that's one way that we're making sure that those teams are able to consistently come in and book time to test and just test, and they're able to verify their own features on a regular basis. When we run the really big tests with just regular behaviors and not necessarily running through formations and automating that whole process, we have done a mix of things. We've had manual QA run through an entire regression suite, especially for the really big tests. So we'll get up to 2 million users, which takes up a considerable amount of time. And then all of QA will just like jump on and try to test everything. And then it's a whole process of finding the right team owners for the right features that are being impacted, giving them access to all of the metrics that we've logged during that time. Ideally, we contact them when we see the regression while the load test is running, and they're able to like switch off of whatever they're working on and come actually visually see it. That doesn't always happen, but because we've made this so easy and fast to spin up, and we log so much content while we do run these tests, engineers are able to usually pretty like quickly hone in on the problem. And then next time we run a big test, we're able to verify it.
Awesome, thank you. The next question comes from Tina, and the question is the following. What are the KPIs that you measured during your test besides checking that the system doesn't crash?
Ooh, well, we definitely like make sure at the end of the week that we haven't blown through a significant amount of budget with in terms of AWS costs. We have a bot actually that like tells us Mondays how much money we spent last week on tests. So that is something that keeps us honest. Thankfully, it hasn't been anything that we've needed to worry about too much yet, but that keeps us honest. And then we look at latencies. We look at a lot of API latencies and success rates. And so that's where you can see, if I scroll down, see like we're seeing peaks in P99 latency for some of these APIs. Obviously, if it takes 50 seconds for the API to come back, that's not great. We should probably be investigating that. Overall, we look at, honestly, if P50 is pretty good, then you know, it's not, usually these are terrible outliers, these like 50 seconds. And because our load test stack doesn't quite run in production, it's as close to production as we can probably possibly make it, obviously, because we want real fidelity in the results of our tests. But we're constrained a little bit more in terms of web app backend resources than in real production. And so sometimes that also has an impact. At the 25K range, wouldn't really expect it, but so latency is definitely something that we look at, and success rates are huge things that we look at in terms of success. And then when we're running specific formations, what we want to verify, usually most of the time, the teams have set up rate limits in place preemptively, and they want to test that those actually get triggered. And so that's something that we'll test for and ensure actually happens. And we'll also look at API latencies during that time and message fan out. That's a huge, huge one, because again, that one message, if there's 200 active clients, can turn into 200,000 messages on the way out. And so that's another one that we look at. One reaction on one message when there's 300,000 connected users turns into 300,000 messages being sent over the WebSocket.
Yeah. That's a lot.
Yeah, it's a lot. So when you think back to like this other channel, right, where we had 113, 111, there's 2.5 million people in this channel. So that turns into a lot of messages being fanned out.
Wow. Okay. Another person is asking, where do you get the base frequencies from
Yeah.
for your behaviors?
So that's all pulled from data analysis that we've automated on real life customers. And so I can't show this for compliance reasons, but we've built an entire dashboard in our data warehouse, which lets us specify a day of the week and hours that we want to look at traffic for and provide a team ID. And so we'll take a look at some of our busiest teams, and we'll plug in that data, usually peak time for Slack usage, regardless of what company you're at or what region of the world, is your Tuesday morning for whatever reason. And so the way that we do it was we normally look at Tuesday morning period because that is peak time. And it gives us all the API frequencies, which are what we put into the behaviors for both the web API and the Edge API. And from that, well, we'll just export this big CSV that it gives us. And then we wrote a script that generates this file from that output automatically. And then we can upload this file into the test when we're running it by default, and we can upload it here. So by default, when you start a load test, it uses this default config because it's easier to just have a default set of things that you rely on and it just boots. But if we wanted to completely change this model and say strip out half of the behaviors or turn them up by 100%, we could tweak this file, re-pull the data from the data warehouse, and then upload that here. And then we'd immediately see the COI pick up those new behaviors. And then we'd see that impact in changes directly to, say, the number of web API calls that are being made.
Great, thank you. There's one more request from Dragoslav for the links from your slides. So I don't know if you're in hopping mode. If you are in the platform, you can just come to the orange stage and send in the links. We can do this afterwards. And I think we're out of time actually with the Q&A. Fantastic questions, everyone. And thank you so much
thank you
for answering all of them in such detail.